Howdy everybody. Today we're going to discuss the mean value theorem. In a nutshell, the mean value theorem tells you that the average rate of change of a process is always realized as the instantaneous rate of change at a particular point. The mean value theorem states that if f of x is a continuous function on the closed interval from a to b, and it's differentiable, meaning that the derivative exists on the open interval from a to b, then there exists a value, x equals c, some x value, that lies strictly between a and b, such that the derivative of f at c, f prime of c, is equal to f of b minus f of a divided by b minus a. What in the world is this saying? Let's start with the right-hand side. What is that number? Notice that this is precisely the change in the outputs, the y values of the function, over the interval from a to b. That's the numerator. And what's the denominator? That's exactly the change in the x values over the interval from a to b. So this is delta y over delta x. This is a slope of a secant line. This is the average rate of change of the function on this interval. So the right-hand side of this equation is exactly the average rate of change over the entire interval. What's the left-hand side? F prime of c. Well, that's the derivative. That's the instantaneous rate of change. At this particular point, x equals c. So what's the theorem saying? It's saying that if you're looking at some interval and you find the overall average rate of change, then there's always some point in that interval, some c value, where the instantaneous rate of change exactly matches the average rate of change. Notice that the theorem is not saying that the derivative is always equal to this value. It's just saying that it's equal to this value at some point. Let's illustrate the mean value theorem. What is it saying graphically? So suppose that the graph of our function f looks something like that. And it's defined here on the interval from a to b. Very good. Well, first of all, what is the average rate of change? What's the right-hand side in the mean value theorem? It's the slope of this secant line connecting those 2 points. So I claim that the slope of this line is precisely the average rate of change over the entire interval. That's because the height here is the change in the y values overall, whereas the width, the run, is the change in the x values. Okay? And now the mean value theorem states that we can find some c, maybe multiple c's, where the derivative at c, the slope of the tangent line, is this average rate of change. So the mean value theorem guarantees that there's some point, looks like about here, where the slope of the tangent line exactly matches the slope of the blue line, the average rate of change. So in other words, the sort of total slope representing the average rate of change is realized in an instant at some particular point c. So the slope of the tangent line, the instantaneous rate of change at c, is the slope of the secant line over the entire interval. It matches the average rate of change. Now in my example, there's actually another point that'll do that as well. So that point where the tangent line has the exact same slope again is another possible value for c. So in this example, we see that we can have more than one c that works. That might happen, that might not happen. Regardless, the mean value theorem asserts that there's at least one such c. There's always at least one c where the instantaneous rate of change realizes the average rate of change.
And now we're gonna pour powdered milk in our 2,000-gallon cereal bowl. It smells like milk. Innovation.
Let's verify the mean value theorem for a particular example. We're going to use the function f of x equals the natural log of 2x plus 5, and we're going to look at that function over the interval from 0.5 to 10. So what does the graph of this function look like on the interval in question? I'll just give a sort of rough sketch of the graph. This is 5, this is 10 on the y-axis. Yeah, close enough. That looks about right. So the graph of this function, the natural log is increasing, but it increases ever slower. So on this interval, the graph of this function f of x will look something like that. And what do we mean by verify the mean value theorem? What that means is we're going to find a specific c value for which the mean value theorem holds, that equation that we just saw. So in other words, that purple line, the slope of that purple line represents the average rate of change over the entire interval. Let me write that down. So the slope of that line is going to be the change in the y values divided by the change in the x values. In other words, it's going to be f of 10 minus f of 0.5 divided by the change in the x values. That's 10 minus 0.5. That's the average rate of change over the entire interval. To verify the mean value theorem, we're going to find a c value where the slope of the tangent line, the derivative, is the same as that number, that slope. And just based on the picture here, it looks like it'll be right around there. So that's going to be the c value. We expect that that c value is somewhere a little bit closer to 0.5 than to 10. So the slope of that other line is going to be the same, and that's going to be the derivative of c. What are we trying to do when we're trying to verify the mean value theorem? That just means that we want to find a value of c for which these two numbers are equal. We're trying to find a value of c that makes f prime of c equal to that overall average rate of change. Okay, so to do that, we first need to compute this number. Let's get right to that. So what is f of 10 minus f of 0.5 divided by 10 minus 0.5? What is that number? Well, first we got to plug it into the formula for the function up there. So we're taking the natural log of 2x, so it'll be 2 times 10 plus 5. That's the value of the function at 10. And then we should subtract the value of the function at 0.5. You know what? This is no good. I ran out of room on my page. Let's scratch that out and scroll down and start over. So we're looking at f of 10 minus f of 0.5 divided by 10 minus 0.5. Looks good. So the value of the function at 10 was the natural log of 2 times 10 plus 5. What's the value of the function at 0.5? Well, that'll be the natural log of 2 times 0.5 plus 5. So those are the two outputs. Those two numbers represent the y values here and here, the outputs of the function at the beginning and end of the interval. 10 minus 0.5, that's the width of the interval. That's going to be 9.5. Okay, what happens in this fraction? Notice that here that minus sign is being applied to everything. So we have a plus 5 and we have a minus 5. Those cancel. So now multiplying 2 by 10, we have natural log of 20. And then what's 2 times 0.5? 0.5, that's 1/2, right? So if we multiply 1/2 by 2, we're looking at the natural log of 1. Great. Now we need to remember, what is the natural log of 1? Well, remember, natural log, that's just asking the question, what do I have to raise e to in order to get the number 1? E to the what equals 1? The answer is 0, right? The answer is 0. Why is that? Let me make a little remark here. That 0 is coming from the fact that e to the 0 is equal to 1, right? Anything raised to the 0 power is 1. And so reframing that in terms of the inverse function, 0 is equal to the natural log of 1. That's always true. Okay, great. So we found our average rate of change. It's the natural log of 20 divided by 9.5. That's great. That's the right-hand side of the mean value theorem. That's the average rate of change on this interval. Okay, so remember we're trying to find a value of c such that f prime of c is equal to that average rate of change. We're trying to find a moment in time when the instantaneous rate of change is equal to the average rate of change. To do that, we need to, first of all, compute a formula for the derivative. What's that? Well, what's the function we're taking the derivative of? It was natural log of 2x plus 5. Okay, what's the derivative of that function? Well, here we have natural log of 2x. We got to apply the chain rule, right? Because that inside is itself its own function. It's 2 times x. So if we take the derivative of the outside function, the derivative of natural log is just 1 over whatever the input is, in this case 2x. But then we need to multiply by 2. That 2 is coming from the chain rule. If we take the derivative of the constant 5, we get 0. So that calculation of the derivative of natural log of 2x came from the chain rule. The 2 is the derivative of the inside function. The 2's cancel, and so we find that this formula for the derivative is just 1 over x. Right? I'll write that right here, fit that in. The 2's cancel, we get 1 over x. So we need to solve for when that's equal to the natural log of 20 divided by 9.5. And here I'm going to use c because, in the statement of the mean value theorem, we use the letter c. So we're trying to solve for c. I could set it up in terms of x, of course, but let's use c. We want that to be natural log of 20 over 9.5. So we just need to solve for c in that equation. Well, heck, that's not so hard. We just need to flip both fractions, right? We just take the reciprocals of both sides. We'll have c on the left, and now flipping that fraction, we get 9.5 over natural log 20. So that's the answer. That's the c value that works. If you put that in a calculator, it's a little bit over 3. So that is the value of c for which the mean value theorem holds. And you can see that this matches the graph that we drew earlier, right? Remember, we're trying to find a point where the slope of the tangent line is exactly the same thing as the slope of the secant line connecting the starting and ending points. And we said that c should be right around there, closer to 0.5 than 10. And indeed, right around 3 looks about right. So, based on the graph, our overall answer certainly is sensible. That is the correct spot. That's the spot where the instantaneous rate of change is the average rate of change.
What is a giant cereal bowl without cereal? This is now the world's largest bowl of cereal.
We now ask, why do we need the function f of x to be continuous on the closed interval from a to b and differentiable on the open interval from a to b in the mean value theorem? Why are these hypotheses necessary? Well, I'm going to show you using examples that if they fail, then there might not be a c. In other words, the theorem might be false. So there might not be a c that works. Okay. So for our first example, let's address continuity. So our function f of x is going to be 1 when x is strictly less than 3, and it's going to be 5 when x is bigger than or equal to 3. And we're going to consider the mean value theorem on the interval from 0 to 6. So that's our A and B. What's this function look like? Well, I'll only draw it from 0 to 6. That's all we care about if we're applying the mean value theorem on this interval. For x values up to 3, it's constant at 1. So if that point has height 1 along the y-axis, f of x is 1, it's cruising along, it's 1, and then it doesn't quite make it all the way to x equals 3, right? Because at x equals 3, it jumps up to a value of 5. So here it is up at 5. If you plug in 3, you'll get 5, and then it cruises along until it reaches 6. We're only going to consider this function in between 0 and 6. All right, so that function is clearly not continuous. There's this big step discontinuity at 3. What would the mean value theorem say? Let's first just think about it graphically. The secant line from the start of the graph to the end of the graph over this interval, that would be that purple line. So I think it's intuitively clear that there's no tangent line that's parallel to that purple line, right? So in other words, the mean value theorem fails. There's no spot where the instantaneous rate of change, the slope of the tangent line, is exactly this average rate of change, this average slope given by the purple line. So there is no x value c in this interval for which the statement of the mean value theorem holds. That's my claim. And to make this absolutely precise, let's see what the mean value theorem would give us if it were true. What is this average rate of change for this function? Well, f of 6, that would be 5. F of 0, the value at 0 is 1. So the delta y over delta x is 5 minus 1 over 6. That's 4 over 6. That's 2/3. Okay? So there's no spot on this graph where the tangent line has slope 2/3. Indeed, you can compute that the derivative is just 0 for all these spots where it's a constant function in between 0 and 3 and 3 and 6. So it's 0 if x is less than 3 or bigger than 3. And in fact, it does not exist at x equals 3, right? Because of this continuity. And regardless, there's no value of this derivative that's going to give you 2/3. It just doesn't work. So the overall point I'm trying to make is that the mean value theorem fails for this example. And the issue is precisely the lack of continuity. So that's an explanation of why we really need this hypothesis that the function is continuous on the closed interval. Okay, what about this differentiability hypothesis? What can go wrong with that? Okay, well, let's do another little counterexample, as they're called. Let's consider the function absolute value of x minus 3. And again, we're going to look at the interval from 0 to 6. What's that function look like? Well, it looks just like the absolute value function, but notice that I've subtracted 3 from the x-coordinate. That shifts the graph of the absolute value function to the right by 3. So this function looks just like absolute value. It starts at a height of 3, it goes down, it hits the x-axis, and then it rises back up. This sharp V shape. Remember that because of this cusp, this function is not differentiable at 3. So f of x is not differentiable at that midpoint of the interval at x equals 3 because of the cusp. Because of that sharp corner. Okay, well, what would the mean value theorem propound? suppose in this case, what would it tell us would happen? In this case, the mean value theorem would be about this secant line, if you like. The slope there, the average rate of change, is 0. Delta over y over delta x in this case is going to be 0. Here, let's compute that directly from the formula, from the mean value theorem. So in this case, f of 6 minus f of 0 divided by 6 minus 0. Remember, that's our formula that the mean value theorem is all about. What's f of 6? That would be 3. F of 0, what's that all about? That would be 3. So we get 3 minus 3 over 6. The delta x, the change in x is 6. Indeed, that's 0. But there is no value of c for which the derivative is 0. Right? What is the derivative of this function? It's minus 1 for these points, because that line has slope minus 1, and it's 1 for these points, because that line has slope 1. Let me record that down here. F prime of x, its only possibilities are minus 1 and 1. That's for x values less than 3 and bigger than 3. It's never equal to 0. The derivative cannot be equal to 0. It's only minus 1 and 1. And so we see that the mean value theorem also requires this hypothesis of differentiability. That's why this example fails. It's because of this cusp. It's because it's not differentiable. So you really need continuity and differentiability to apply the mean value theorem. Both of these hypotheses are necessary.
You are now in the world's largest bowl of cereal.
Everyone, I cannot have you dying on my watch, so we're going to do a little bit of exercises. We're going to start off with just some little squats. You know, the obliques, we're going to hit those real quick, back and forth a little bit.
Yeah. Let it out, guys.
There we go. Now bend over and touch your toes.
Yep, not happening.
Just kidding.